Welcome to Study Loop.
So for this problem, we have an infinitely long wire that has an unknown charge density, and we use a voltmeter at two different points. So I'll call this point 1, I'll call this point 2, and we know that if we use a voltmeter between these 2 points, the voltage is 575 volts. 75 volts. And we know some distances. So this distance here is 2.5 centimeters. And then this distance between the points is 1 centimeter. And we're just asked to find what is the lambda, what is the charge density of this wire. So first we need to find the electric field from this wire. So we can use Gauss's law. And what we'll do is we'll just draw a nice symmetric Gaussian cylinder around this wire. The electric field points radially outward, and dA also points radially outward. But on these end caps, dA points left and right. So on the end caps, dA and E are actually perpendicular, and so therefore the integral for Gauss's law, lambda E dot dA, equals to Qn over epsilon naught, this integral will be 0 on the end caps. And since this is symmetric, it has a constant radius. Our Gaussian surface has a radius of r. The electric field will be a constant. So we can pull the electric field out, and this integral simply becomes E times the area of the side of our cylinder. So the reason that it's just the side of the cylinder is because of these end caps were 0. So now we don't have to worry about them at all. And then the charge enclosed will simply be however long my cylinder is, my Gaussian cylinder, times the charge density. This will just be lambda L. Now, the area of the sides of a cylinder is just the circumference of a circle, so 2 pi r, times the height of our cylinder, so it's just L. And then this tells us that the electric field outside of this infinite wire will simply be equal to lambda over 2 pi r epsilon naught. And now that we have our electric field, we want to actually figure out what the voltage is at point 1 and point 2. Since we know the voltage between them, we can find out lambda using that. So what we'll do here, I'll draw another little picture down here. We want to do a line integral between these two parts. So we know the electric field is pointing radially this way. So I'm going to choose my path integral to be along a path that is parallel to my electric field that connects these 2 points. So the reason I choose this path is because when they point in the same direction, it will make my integral the easiest. So now that we have this set up, we can calculate that delta V is equal to minus the integral of E dot ds. So you can see now, since S and E are pointing in the same direction, this dot product just becomes the magnitude. So this is just minus the integral of E ds. So now we want to plug in E, and we want to put some limits on this. So this will become delta V equal to V final minus V initial, so V at point 2 minus V at point 1 is equal to minus the integral of R at point 1 to R at point 2, because this is our initial and our final. And now we can plug in the electric field. So the electric field is lambda over 2 pi epsilon naught R, and then ds we can say points radially, so this just becomes dr. So now when we do this integral, we're just going to get Vp2 minus Vp1 is equal to, well, we can pull out all these constants, and then the integral of 1 over r is simply natural log. So this will be the natural log of r2 minus the natural log of r1. So now we know these distances, and we also know this voltage difference. So we can actually solve for lambda. And I'm also going to so let's first combine these natural logs. So lambda over 2 pi epsilon naught. And when I pull the negative in and then use a log rule, that the subtraction of two logs can be rewritten as a division sign, we simply get that it's natural log of r1 divided by r2. And this is Vp2 minus Vp1. And so now we can just, and also Vp2, since P2 is further away, the voltage will be smaller. So this Vp2 minus Vp1 is going to be equal to negative 575 volts, because the voltage will get lower as we get further away, since the electric field is getting weaker. So now we can solve for lambda, and with just some algebra, we get lambda is equal to negative 575 volts divided by natural log of r1 over r2 times 2 pi epsilon naught. And if you plug all this in your calculator, you get that lambda is equal to 9.5 times 10 to the negative 8 coulombs per meter. So now we have the charge density of our infinite wire. And then for part B, it's asking us about if we move these points away, so we have our infinite wire, and then we pick two new points, P1 and P2, if these are still 1 centimeter away, will the voltage between them still be 575, even though this distance is r greater than 2.5 centimeters? So the answer is no. So first off, you can see this simply by plugging in to our voltage equation. So delta V that we got was lambda over 2 pi epsilon naught times natural log of r1 over r2. So if you were to simply plug in r1 and r2 that are bigger than what was in part A, you would get a delta V that is smaller. The other way to think about this is that the electric field is related to 1 over r. So this point at P2 actually dies off faster than the point at P1, and so therefore the voltage difference between these 2 points will be weaker, since the one that's further away is diminishing faster. But all you need to know is that no, the voltage will not be negative 575 volts. Delta V in this case will be less than 575 volts. And then finally, for part C, we're now asked that if we have this wire and we have a point 1 here, a point 2 here, and they're the same distance r away, what will be the voltage between these 2 points? So you can just go back to our nice formula. We have lambda over 2 pi epsilon naught natural log of r1 over r2. But if these r1 and r2 are the same, you get natural log of 1, and natural log of 1 is 0. So voltage between these 2 points will be 0.